He's currently visiting Taiwan, and originally from University of Oregon, and he will tell us how exciting this robot is.
Hello? Okay. I'm doing my sabbatical at NTU, so if anybody wants to chat about machine learning or other things at work, please find me. There's two, as far as I know, two machine learning talks. The next one after the break is David Shi, and so we're going to try to give you some sense of what's going on in machine learning and high energy physics, and we have different kind of approach. So my approach is to try to understand these techniques. So it's a little bit more about not an application, but more about trying to understand why, after you have an effective application, can you learn some science from it? Can you learn the physics underlying it? Because as I'll try to present, machine learning is very effective, but they're kind of like black boxes. They're very difficult to understand how they are being effective. And I'll try to give you some examples of that. And David will give an example of how effective it'll be. So in some senses, this picture is supposed to be provocative. You know, some people say that robots will replace everybody, right? So here, this robot's doing math and all sorts of things. Okay, but maybe if we can learn how to learn physics further, then we can work in connection with it. Okay, so this is work in collaboration with my Oregon collaborators, Tim Cohen and Brian Austin. And if anybody's looking for a good high energy phenomenology postdoc, Brian's on the market with this. Okay. All right. So let me give you the outline talk. So it's try to give you, try to motivate why machine learning is very effective, but there's this open question of how do we understand why they work, and in any given instance of an application, how you can understand them. Okay. And so we have a kind of a physics-motivated one where maybe you're interested in what we're going to focus on classification problems. You want to understand what are the important variables that make the machine learning classifier classify well between two types of events. And so here's a process called data planing that we're suggesting is a good way to test if any given physics variable is important in terms of that classification problem. And I'll give you a simple collider application just to illustrate the point that where we already know the physics, but to show how this can be used. So it's just a demonstration, and we're working on kind of follow-ups where we look at more complicated problems that really require a neural network. Okay? So that'll be in the future directions. I'll talk about some. So I want to start first in the broad sense, because probably that's certainly the things that are kind of the hottest in terms of the media. Machine learning is everywhere. And here are just a few examples. There's obviously more recent stuff as well. Here's Go Go was a problem, a game that was not supposed to be, amenable to computers, and deep learning has overcome that. Here's kind of an interesting kind of cute thing where you can generate fake photos now of celebrities that you think like they're so realistic they have to be these people that was in some movie you saw, but these are just generated, they're fake. And here it's kind of like you're playing off two neural networks, one that's supposed to generate the fake photo and one that's supposed to tell if a photo is fake, and you kind of use them in a feedback loop to try to make better and better fake photos. And here, machine learning is also becoming more a part of our lives, right? Automating many of the things that that we need to get done. For instance, in here, your Google Photos, if you open it up, you can see things classified. It's not perfect. This is classified as a horse for some reason, but other things worked out pretty well. Like graduation, butterfly, and surface. So machine learning is super effective. It's become more and more important. Part of many things that affect us every day. But there's an open question about how they work and what are they uncovering. Right? For instance, if you're a Go master, you might want to use this stuff from DeepMind to try to understand the game better and learn how to play better. And you can observe matches they'll play, and they'll do moves that you wouldn't normally expect. But it doesn't tell you why it did it. It doesn't tell you the strategy. It can't give you some concise way. It can't write a book about how now I've mastered Go, and here's how you should play. And so it's kind of unsettling, right? Or it's kind of unsatisfying. It works well, but it can't tell you why, right? And so this is an important question. And it's also becoming more and more important recently because people are asking hard questions to people in the tech industry, how their algorithms work, do they have bias, are they doing things that we should be worried about? And to be honest, for the most part, they can't answer these questions directly other than saying we're not trying to introduce bias, but it's really hard to kind of unpack these algorithms and try to understand them. And so it's something that's really in the early days, even in the tech industry. And so there's work in that way, in that direction, but I'll tell you about our direction in physics. Okay, so but before I talk about some of that, let me just talk about how machine learning is affecting high energy physics. And there's many different applications that mirroring the kind of the more popular tech applications. There's many things that are actually piggyback on that. For instance, here's a way to better select for top quarks using a deep neural network, and it does better than things that use good physics variables like n sub jettiness. David, I think, will talk about his top tagger, which also uses a neural network based on the image of a jet, and it outperforms, right? So it does better than the physics that we know. Okay, so there's also a way, so it can not only replace theorists in the sense that it knows more theory about top quarks than you do. It can also replace phenomenologists in the sense that you give it a new physics model. As a phenomenologist, you would know that there's some interesting kind of variables here of like different resonances in this cascade. But if you do deep neural network, just applied on kind of the very basic low-level kinematic information, it's sensitive to the information in those kind of physics variables you think you already know about, but also knows other things as well. And so you don't have to kind of design a kind of simple cut-based approach. You can just use a deep neural network and use that to look for new physics once you know what the model is. And this is an example where it's not kind of in terms of trying to find something. It's more about kind of getting neural networks to do something like the fake photos. Here it's a way to generate fast detector simulation so that it tries to fake a realistic detector simulation but does it in a much faster way. So it's kind of just an overview of some of the ideas that people have been doing in machine learning for high-energy physics. Okay, so I want to try to understand some of the machine learning applications. In particular, I want to understand classification. So this example of the top tagging that I just showed earlier, here you can just to emphasize again, here's how often you tag a top quark jet versus the mistag rate. So you want to be lower on this. Sometimes it's plotted the other way, like it's a background efficiency. But here it's kind of inverted. You want to be in the lower right to have a better tagger here, right? Because you have, for the same efficiency, a lower mistag rate. Okay, so here's the neural network tagger, the blue one, and it does better than kind of the kind of physics-motivated variables. So it's clear that it's effective, but if you want to know what is it actually kind of uncovering, you can't really tell because a neural network is a completely analytic function of the inputs, but it's not in a kind of form in which it's easy to understand. Okay, so it's kind of it's just unsatisfying. It's effective, but you can't learn about it. Right? So if you're interested in top quarks, the physics of boosted top quark jets, it doesn't tell you what's going on beyond n sub jettiness. And so in these scenarios, maybe it's possible that this this classification using a neural network is learning new variables or subtle correlations that we don't know about. And so for theorists, that's very interesting because maybe there's something we just don't quite understand about QCD. But for experimentalists, it's also important because if you want to be competitive and try to get more top quarks, you want to use a tagger like this. But you also want to validate and make sure that there aren't some large systematic uncertainties into the things that go into it. But it's hard to tell if you don't know exactly what's relying. And so I mean, some people have to work hard. For instance, like in the Atlas Susie group at Oregon, they often will use a machine learning approach, but then to validate it, they kind of unpack it and try to figure out what those variables are. So this is an important question, both for theorists and experimenters. Okay? So I want to focus on classification. How do you determine something like top quarks versus some light quark jets or something like that? And so this is just it's called classification. And this is kind of a very simple-minded example. Blue types of events versus red types of events. And here it's a very simple 2D region. Right? Two inputs that tell you possibly what if it's a blue or red event. Okay? And so neural networks are very good at performing this type of problem of trying to differentiate between blue and red. And so the way you do it is you set up a neural network. And this kind of architecture, I think David will say something about this as well. But the basic idea is it's a function of a particular type. Okay, so you have the inputs of whatever you're trying to use as a way to distinguish between two particles, your x and y in this 2D example. There's some parameters called weights, which connect them to nodes, where the nodes receive a linear combination of the things weighted by the weights and also maybe offset by a bias. And then you apply an activation function, which is a nonlinear function. It could be something like there's something called a sigmoid, there's something called a rectified linear unit. But there's some choices on what you do for nonlinearity. And you have several nodes here. You can have different layers so that these nodes go into other nodes, etc. But that's basically what happens, and it goes finally to an output. Here for a classification problem, you probably classify like blue is 1 and red is 0, and you use that as a function to try to predict how close you are to blue or red. Okay. All right. So that's basically what a classification approach by neural networks is to design this thing that's supposed to, given the inputs, tell you are you closer to the blue or the red. Okay. And so why does this work? Why is this effective? Is because neural networks have, there's a theorem you can prove that a neural network can approximate any function. And so I think you can do a very simple 1D example where you can do it by step functions by choosing certain types of nodes with different activation function. I can talk to you about that offline. But basically there's a way to approximate any function, right? And so basically think about the neural network, trying to make it demystify it a little bit, is that it's a very interesting arbitrary function of the inputs to some output. And the way you figure out what are the good parameters to try to predict if it's blue or red is to use some training events to try to figure that out. Okay, so the why it works is because you can approximate any function, and then you use example points or events to kind of train it. What are the parameters of these weights? What are the biases? Okay, so if you do that, something like this will form some type of boundary where you can choose to cut to try to figure out where blue and red are. Right? So that's the training part, but I won't talk about too much about it. Okay. So neural networks are great for classification, and we want to understand how to kind of understand them. Okay, and so here, let me give you something that's maybe a little bit more motivated in terms of like what you might try to understand from the physics. So here are these two classes of events. Again, it's a 2D input, but I clearly try to make it so that the rate data is a circular region of red and outside is blue, right? So I want this to kind of try to look for something that's a nonlinear function of x and y, just the radius of a circle, right? And if you do a deep neural network, you get something like that. Okay, so this is to illustrate that in certain cases you can try to interpret what a neural network is doing if you kind of figure out what the right parameters basically look at. If you're looking at y and x in this case, it looks like a circle. It looks like it's learned radius. And people will kind of use this kind of, I would say it's a sloppy language that it's learned radius. Because if you look carefully, it's a polygon that kind of approximates a circle, right? And in some sense, the discreteness of this kind of neural network that forces you to have this approximation. It's not going to give you just x squared plus y squared equals square root of it. It's going to do something approximate. And so, if it's simple enough, you can interpret it. So if you know the kind of way to slice it and look at it, you know the right variables, and you can kind of say, well, maybe this is I can understand this is radius that's probably 25. Okay, but this obviously becomes more difficult the more inputs you have, the more kind of features you have that distinguish between red and blue events. This becomes more and more challenging. We have to develop other techniques to tackle this problem of interpreting a classification, a machine learning classifier. Okay, so there is kind of an approach that people have been pushing to kind of say like, that does this, it doesn't quite do that. I just want to use this as a kind of counterpoint of what we're trying to propose. It's something which a lot of these had kind of weird names, so we made our own. This one is kind of like saturation of discrimination power. So here is where the concept is you want to know if a classifier is reconstructing something like a radius in the previous example. So the idea here is to add that information to it. Give it as part of the events. Instead of just x, y in the previous example, give it also the radius at the same time, and then retrain. Okay? And then the idea is you check to see if it still is, if the discrimination between red and blue improves or not. If it doesn't improve, then the classifier was sensitive to that information. So for example, this cascade event, here are some of the example deep neural networks they use. Here, is if you give it just the kind of invariant masses, the high-level variables, kind of the Lorentz invariant kind of information there. If you give it the high-level variables, it does as well as this. Here, better is to the upper right, sorry. Notice that if you just give it the low-level kinematic information of the decay products, it actually does better. Right? So you would think that, well, since it's doing better, it's somehow sensitive to this, but something in addition, right? The way you test that is to add, have both the high level and the low level variables. So you see that it does just as well as the low level. And so that seems to suggest that the information that's in the high level variables was already kind of this deep neural network had already kind of reconstructed that just based on the low level variables. Right, so it seems like the deep neural network is already able to reconstruct kind of Lorentz invariant information based on this saturation. So it seems like it's saturated by when you add the high-level variables, so it's already in there. So in this case, I think it's because we know some of the physics that these are obviously important variables that we would have to think that a deep neural network based on the low-level ones has to reconstruct some of it. But just because it saturates doesn't mean it's important. It just means that it's not. That was already sensitive to it may not be important to the problem. So that's part of the reason why we think it's not quite right to say that this tests whether, say, a variable is important to a classification problem or not. But I still think it's pretty cool in this example to see that the deep neural network is capable of learning Lorentz invariant information without knowing anything about Lorentz invariance. It learns it from the training events. Okay, so our approach is something we call data planing. Okay, and this was suggested in an earlier paper, and we kind of more fully explored it. So planing is a woodworking technique to kind of smooth out a surface, and we kind of understand why that is. So what's our idea is to, instead of add like a variable like in the previous example of saturation, here we're going to try to remove it. And we remove the information, then we're going to retrain the classifier and try to see, was that information important by looking if the performance degrades. Right? So we're removing some information. If it degrades, then it was important information. Right? So that degradation tells you how important that variable is. So the idea is very simple. All you do is reweight the events, but you have to decide what kind of information you're trying to remove. Okay, so you have to choose a certain variable. If we want to think about physics examples, a certain physics variable, for example, the radius in the simple circle example, or this cascade sum invariant mass. You remove that and try to see how poorly the new classifier based on those reweighted events does. So the idea is very simple. You take some distribution where it looks of the red and blue events, and you make both of them flat in that variable. So you reweight the events, make them both so that they're featureless in this variable, and so you're applying different weights to both the blue and the red. They're separate weightings to do that. And so there's no way now that when you retrain a neural network based on these reweighted events, there's no way for this variable to be, for this neural network be sensitive to it. So that's how we remove the information by this planing technique. Okay, and obviously the planing is just removing the smoothing technique. Okay, so let me illustrate this with a collider example. Here, this a simple example where we can understand all the physics so we can kind of really see, do we remove the information we know is there? Okay, so that's why we chose a simple example. And so this is a classic, simple signal at a hadron collider, a Z prime. So we have two protons coming in. They annihilate into it. Well, the quarks annihilate into a Z prime. It just goes to E plus E minus. And here, just for kind of cleanness of what we want to compare between signal and background, we want to just look at the off-shell photon background. Okay? Just because we're going to do examples where the chiral information of the couplings are could be different from the photon, which is just vector light. Okay, so we have two signal examples. I'll only really talk in detail about the chiral one. But here are the kind of important raw distributions where we do need planing. Okay, so the photon background is the blue. Here's the variant mass of the electron positron, right? And it's just a falling background for the photons. The resonance of the Z prime has a nice peak, right? So this is obvious. And here is the rapidity of the electron. And here you see that there's now two, because they're overlapping here for the Z primes. Here now there's both a red and a green, and those are two types of Z primes. One is vector-like coupling, like the photon, and that's why it's kind of close to the photon, which has a similar shape. But the left-handed chirally coupled Z prime to both electrons and to the quarks has this double hump structure. If you look at the positron pseudo-rapidity, it looks very similar also. The photon and the vector Z prime, very similar. And the chiral Z prime looks different. Okay, so let's just reweight the events to try to remove this obvious information of the mass and see what happens. Okay, so that's just the plane in this, so it's even in both the signal and the background. So we reweight all the three different type of distributions, the photon, the two types of Z primes, so they're flat. Okay, what's interesting about that is what happens to these other variables. So there's some correlations, there can be correlations between the pseudo-rapidities and the mass, and an interesting thing happens, right? So here, the things that were slightly different in pseudo-rapidity, right, the vector-like Z prime and the photon, now are indistinguishable. And so because this is why planing is a little non-trivial, because otherwise we would just say, well, of course it's important. It's just that this very stark difference between signal and background. Here you see that once I plane in one variable, I may be removing all the information to distinguish the Z prime vector-like from the photon. And that's why these things line up, and the pseudo-rapidity of the electron and also the positron. Okay? So there's no way to distinguish this once you got rid of the information. And so even though it looked like there was lots of information separating a Z prime of a vector-like coupling with the photon, it's really just the mass. Once you remove the mass, it's all gone. But if you have the chirally coupled one, you see that there's still residual information. So there's still more information that you should try to remove. And we know, right, because there's going to be angular, kind of angular distribution of different reflected. Okay? All right.
Yeah. Yeah. What you're making is that in the middle two panels,
yes,
the alpha and the green and the blue are a little bit separate.
Right.
The bottom of the right now.
Right. Once you reweight the events, it's not only done something. I mean, our intention is to make this flat, but it also does subtle things potentially to other variables by reweighting. And so that's the kind of key thing. Is once I essentially remove the information mass, it's removed. There's no other information, and that's not obvious, right? Once you
Yeah. But the untrained eye kind of goes together with the top panel too.
That's true, yes. And so it must be things that because we have this kind of extra events here that we're just being and once we do with it. Okay. So what we know now, I mean, just looking at the distributions, and I already know enough about the physics to have already guessed this, but that distinguishing a vector-like Z prime for a photon, the only important information is the mass. because the couplings are the same, right? And that's what was borne out by the reweighting. The chirally coupled Z prime compared to the photon has the mass, but also some angular information. So let's see how we can do planing and what happens. And I'll look at the Z prime that's chirally coupled because it has the most kind of non-trivial things I can do. Okay, so this is one of the tables from our paper. And so here are a couple of lines, so let me try to explain what's going on. So there's a lot of neural networks here with some diagnostics for how well they're doing when trying to look for the Z prime that's chirally coupled compared to the photon pattern. Okay, so here what's in this part of the table is what are the inputs that are provided to the neural networks. So here's the forward momentum of the electron and positron. It's being provided to all the neural networks. Whether we add the extra information of the mass is the next column, and we're only providing for one. And then are we planing in the events in any of those variables? In any variables, you will see that we'll do mass and also a difference in relativities. Okay? And there's two types of neural networks for each row. There's a linear neural network, so it only has a single layer inside. Sorry, actually, actually there's no, it's just a single, it's just straight to the output, sorry. And then the deep neural network has three hidden layers, so it's those layers inside. Okay, and in each of these neural networks, we have a diagnostic variable that tells you how well it's distinguishing between Z prime and photon. It's called the area under the curve. It's just one of the possible ways to diagnose this. It's essentially the area under the curve for those, those plots I was showing of different different like compact differences. Okay, so there's a linear and a deep version. Deep one should typically be better because it's kind of, that's where neural networks seem to shine. Okay, so let me show you, so to normalize what that means of what's an area under the curve, if it's a 1, it's perfect, right? It's essentially saying that you have signal efficiencies 1 even though you have no background. And if it's a half, it means that it's kind of not able to distinguish between signal and background. Every time you let in the signal, you let in the background. So that's the two kind of extremes. 1 is perfect, 0.5 is random, yes. So it's a forward classifier. Okay, so now now that you normalize this diagnostic, we can compare some of these examples. So let's compare the first two lines, rows. So the first one is just the typical neural network where I just apply give you an electron positron. I haven't done anything in terms of adding this mass or planing. And here you see that the linear network doesn't do as well as the deep neural network. That's not, here the deep neural network is almost 100%. Right, in terms of the area of the curve, it's like 0.76 for the linear. Now, you get some more information by comparing when you add the mass, right? So this is like that saturation kind of approach I was talking about. You add mass to see if it was already aware, the neural network was already aware of it. And so here the deep neural network is already aware of that information, right? Because it doesn't really improve at all. Right? It improves a little bit. It should, in principle, probably improve a little bit because maybe the training goes a little faster. Already has that information. But it's pretty indistinguishable. It's like the 4th decimal place. There's some our estimate of what the statistical error is, but you shouldn't probably trust it too much. It's just from different realizations of the training. But it didn't improve, so the deep neural network, you could say, was already sensitive to the mass information. In this particular example, we know it's important, and so it's already, kind of reconstructing that information. In the linear one, you can see how much better it improves once I add the mass, right? It goes from 0.76 to 0.94. And so clearly was not sensitive to that information. Once you provide it, it does much better. And so I have maybe some kind of linear approximation of mass, but it's, now with the mass given to it, it does much better. Okay. So that's comparison of line 1 and line 2. This is this other approach called saturation. Okay, now let's compare line 1 and line 3, where what we've done is we have the same inputs, but we just reweighted events, so we plane away the mass information. Okay? Now if I compare here, both neural networks degrade. As you should be, you're removing some information, so it always should in principle be graded by some amount. If it's important information, it degrades by a lot. Okay, so here the linear network drops from 0.76 to 0.63 or so. So it gets worse. And the deep neural network drops by a lot, right? It goes from 0.99 to 0.63. So you can see that the mass was super important for this deep neural network, right? Most of its discrimination power has gone away once I remove it. And once I remove the grand mass, notice that these linear network and the deep neural network are very similar. And so this seems to suggest that whatever information is left is really linear information that you can reconstruct aside from the mass from the formal dimension of the electron model. Okay? So this is just going to give you an illustration of how you can use this as a diagnostic tool. Finally, we want to remove all the information. There's still some remaining information besides the mass because we're not 0.5. Right? So there's some other information. And we know from the distributions and also kind of our understanding of angular distributions that it should be something about the superaffinities. And here we just take the difference of the electron positron and superaffinities and take that back. So we plane away that, and you can see that it's roughly consistent with 0.5. It looks like several sigmas away by statistical error, but don't trust that. More or less, it looks like all the discrimination information is gone. And so this is how we planed away all the information. Now we kind of think that using this procedure, that mass and the superaffinities difference is what would important variables. So this gives you an illustration, an example that we understand how to do this and essentially remove all that. All right, any questions on that? So let me talk about some of the pros and cons of this approach. Okay. So some of the pros that are kind of nice about planing, is that this is degradation of some nice classifier, right? The deep neural network before of the Z prime had like an area under the curve very close to 1. Once I find an important variable and remove it, it drops immensely, right? Compared to saturation where you kind of try to see, did it improve or not? You're already kind of very close to the area under the curve, if it's close to 1, it doesn't change by a lot. So it has a large dynamic range to try to probe if something's important. And in terms of a neural network architecture, you actually don't need to change it because you're not changing the inputs at all or any kind of the number of nodes. You're just changing what the weight, what the events are, and the training data, and you're reweighting them. That's all. Okay, there are some cons that we don't know in the sense that we've only used this in a very simple example. So we need to demonstrate that this is kind of usable in a more realistic neural network situation where you need a neural network. Maybe you'll need to remove many features, many variables. Right? Is this possible to do in more than, say, 2 variables like we've shown? And for instance, in this case, we knew everything. So is it possible to do this if you don't have too much physics intuition about what the variables? So there are obvious examples where you can kind of parameterize what the possible variables are. There's a lot of work that's been going into jet physics about this. So that's some obvious example where we already have a list of candidate variables. You can think of obviously Lorentz invariants as well, and try to systematically remove that. And so we don't know if it's something that's super nice and clean, or if it's an ugly, worked out environment. All right, so we have some future directions we're still exploring. We're trying to address some of these cons by looking at a more non-trivial scenario. Jets are obviously a big thing that we're looking at, but we're also looking at whether kind of uncertainties in the detector simulation are important for this. There's some work that's been shown that it looks like the information in jet saturates at some point in terms of mini-body phase space, in terms of a boosted jet, and that's something we'd like to check by using this planing technique. Obviously, we would love to find a situation where we actually discover this new physics variable and demonstrate that you can do that with this technique. And kind of the thing that we're having a little bit of trouble with, but would be really nice, is can we use planing as a way to test if a neural network has kind of adequately maximized its kind of discrimination. So for instance, can you use the output of the neural network as the planing variable? We're having some trouble in doing that, but that'd be obviously a nice way to just diagnose if a neural network has kind of, has kind of removed all, or kind of has utilized all the information to do discrimination. So let me just conclude. I'm trying to argue that machine learning is important, but also it's crucial to work on also understanding them. And I think it's a nice opportunity to try to use it as a way to understand physics and learn new physics. And this is just one of the techniques of planing that I think there's many things that have been proposed that I didn't have time to talk about, and obviously they can be used in conjunction. And the idea is simple. You just remove information by weighting events and then use the degradation to test if it's important. And machine learning is just going to become more and more part of our everyday experience. And there are still very basic questions there unanswered. So those are the kind of things that I'm working on and trying to address. So thanks.
Questions or comments?
I didn't quite understand something you said at the very end, that you were trying to use the output of the neural net as the planing variable.
Yeah.
Can you expand on that?
Yeah, so you could hope that, it's a simple example, right? For instance, like the circle, right? The neural network output is trying to approximate something based on that radius, right? And so it might be a way to address like one variable that the neural network has found that it thinks discriminates between red and blue. So if you remove that and try to see if it still has discrimination power, it would tell you if it kind of had maximized the discrimination. Right? So the neural network output is itself a variable. It may not be a nice variable, but it's a variable that's supposed to distinguish between the two types of events. So if we can plane in that, it's a way to just diagnose with the neural network that is kind of adequately trained. But it's not in the same sense of learning physics. It's more just a diagnostic tool of the training we're talking about.
Any other comments, questions? Actually,
Yeah, sorry, actually I missed the most part of the talk, but I want to ask about this. Actually, some of my colleagues told me that it's maybe a good idea to use things like language processing or like a recurrent network to deal with particle physics, because the particle physics sometimes, for example, like the Boole fermentation, can be just think of like a way how we formulating a sentence or something, because particles can be like words, and you connect words using QCD. So it's like Obama. So do you have any comment or suggestion on this kind of things?
I mean, there's certainly a lot of work that's gone in that direction, and I'm not super familiar with it. But there's people who have explored that, and so the type of work that I've mostly been focusing on is trying to not apply things like that, but also to try to understand them. And so maybe it could be used in that. This type of techniques could be used in that scenario. I don't know anything about that, but it's a little outline of my strategy.
Could you just comment on, so there's a lot of interest, I think, from experimentalists on having things like mass decorrelated taggers.
Yeah.
Could you comment on the difference between that, what they do there sometimes with an adversarial network, and what you do with the planing?
Yeah, I mean, I think the original name for planing of this uniform phase space was kind of thinking about those things where you didn't want it to learn mass. And so you give like very narrow regions of like training data where it's essentially so small, window and mass that you wouldn't be sensitive to it. We're using it more as a kind of way to test if, say, a mass was important to the discrimination. But you obviously do this as another way to decorrelate, right, or kind of remove that information to make sure it's not being used. And so, I think it's just another type of approach.
Have you done a comparison of which one is more effective, adversarial or just planing?
No. I mean, it's an interesting idea, but no.
I have a question. Is it? I mean, when people writing the code for this neural network, could they add one more thing? Just that when they output, they put a relative importance of each discriminating variable. Then you don't have to do all the planning.
Well, I mean, when I show you that neural network, right? You can write down a formula for it, right? Because it's just a linear combination with all these nonlinear things. But after the deep networks are the ones that are super powerful, right? And by that time, it's already been convolved in all these kind of weird ways. Nobody can understand it, right? So that's why it's not like I just look at the formula and understand it. Some of the other approaches that people have proposed are, in image kind of processing type things, working on jet images. You can look at the types of images, try to use your eye to try and understand it. But also there's ways in kind of people have proposed to look at different late neurons and try to understand what information they're utilizing. And so you can kind of unpack things a little bit like that with that kind of retraining like we are. And so that's why I say like it might be useful to use these in conjunction. I don't think there's anything that's obvious the best approach.
So, any other questions or comments? Okay. So, if not, let's thank Spencer.